January 1945 settled over Germany like a shroud. The Reich was shrinking by the day. Cities burned nightly under Allied bombers. Rail lines lay twisted and broken. Fuel was rationed to desperation. And yet, in a frozen warehouse on the outskirts of Berlin, three ordinary-looking American artillery shells rested on a steel examination table, carrying with them a truth more dangerous than any bomb. They had been recovered from the Ardennes, collected quietly after the German retreat from the Battle of the Bulge. To the untrained eye, there was nothing remarkable about them. Standard caliber, conventional casing, no visible innovation. But the reports that accompanied them told a different story, one that frontline commanders struggled even to describe. American shells, they said, were exploding in mid-air, not randomly, not occasionally, but with terrifying consistency. They detonated above the ground at the exact height required to shred infantry in foxholes, behind walls, or lying flat against frozen earth. Cover no longer mattered. Distance no longer mattered. Every burst seemed perfectly placed, as if guided by an unseen intelligence. German gunners had no answer for it. These shells did not behave like artillery was supposed to behave. Dr. Heinrich Becker understood that immediately. Becker was not a Nazi ideologue. He was an engineer, a career technocrat whose loyalty lay not with slogans, but with tolerances, measurements, and test results. As chief engineer at one of Germany's primary weapons evaluation facilities, he had spent years dissecting enemy technology, British radar components, captured Soviet armor, fragments of American aircraft pulled from smoking craters. He had never seen anything like this. The warehouse was unheated. Becker's breath fogged in the air as he removed his gloves and approached the table. The shells had already been rendered safe, but he handled them with instinctive caution. Artillery did not forgive mistakes. He began with the fuse. The nose assembly was unscrewed slowly, methodically. Becker worked in silence, surrounded by a small team of technicians who understood enough not to interrupt. Every step was documented, every component laid out carefully as if part of a surgical procedure. When the outer casing came free, Becker froze. He leaned closer, adjusting his glasses. For several seconds, no one spoke. Inside the fuse was a radio. Not a metaphorical one, not a crude signaling device, an actual radio set, miniature, self-contained, and shock-hardened, embedded inside an artillery shell that had been fired from a gun producing acceleration forces exceeding 20,000 times gravity. By all accepted engineering logic, this was impossible. Radios were fragile, vacuum tubes shattered easily, circuits failed under vibration. Even Germany's most advanced airborne electronics required careful handling and constant maintenance. The idea that a radio could survive being fired from an artillery piece, travel at supersonic speed, and function flawlessly moments later defied everything Becker had been taught. And yet, here it was. He examined the components one by one. The vacuum tubes were astonishingly small, far smaller than anything German industry could reliably manufacture. They were mounted in shock-absorbing structures so precise that Becker immediately recognized the level of industrial discipline required to produce them. The wiring was immaculate, the soldering flawless, no substitutions, no material shortcuts. There was an antenna cleverly concealed within the nose assembly, a power system Becker found almost elegant in its brutality, a glass vial containing electrolyte that shattered under the force of firing, activating the battery only after launch. No shelf degradation, no power loss, simple, brilliant. This was not theoretical engineering, this was production engineering. The principle became clear almost at once. The shell emitted radio waves as it descended. When those waves reflected back from the ground, trees, buildings, or bodies, the change in signal triggered detonation at precisely the right moment. The shell did not rely on timed fuses or pre-calculated trajectories. It decided for itself when to explode. The implication was horrifying. Foxholes were obsolete. Trenches were obsolete. Every defensive doctrine built on distance and cover was suddenly inadequate. Becker stepped back from the table and sat down heavily. He did not need further testing to understand what this meant, but he ordered it anyway. Frequencies were measured, components weighed, materials analyzed. Every result confirmed the same conclusion. Germany could not replicate this device. Not because German engineers lacked intelligence. Becker knew the men on his staff. Some were among the finest technical minds in Europe. The problem was not ideas, it was reality. Factories were damaged or destroyed. Skilled labor had been replaced with forced laborers who lacked training and incentive. Materials were substituted with inferior alloys. Copper was impure, aluminum inconsistent. Precision had become a luxury Germany could no longer afford. This fuse required perfection, and perfection required stability, scale, and time. The next morning, Becker convened his senior engineers. The mood was grim even before he spoke. He laid out the components, the diagrams, the results. No rhetoric, no speculation, just facts. The question he asked was simple. Can we build this? No one answered immediately. Finally, one engineer shook his head. Not at this scale, not with these tolerances. Another added quietly, not at all under current conditions. Becker nodded. He had expected nothing else. Then one of the younger engineers asked the question that no one wanted to voice. How many of these do you think they've made? Becker looked down at the table again, at the immaculate components, at the confidence implied by their design. Enough, he said finally, that they are issuing them as standard. That single sentence changed the room, because issuing something as standard meant mass production. Not dozens, not hundreds, thousands, possibly more. And if the Americans were willing to place such an advanced device inside every artillery shell, it meant they were not conserving them. They were not rationing innovation. They were overwhelming the battlefield with it. Becker understood then that the fuse itself was only a symptom. The disease was scale, and scale, once reached, could not be bombed away. That evening, Becker requested access to broader intelligence summaries, production estimates, intercepted reports, industrial analyses. What he was about to read would confirm his worst suspicions, and it would make the outcome of the war, in his mind, no longer a matter of strategy, but of mathematics. The intelligence reports arrived on Becker's desk like a silent avalanche, paper after paper, telegrams, intercepted communiques, factory reports, all pointing to the same brutal conclusion. American industrial capacity had reached a scale Germany could no longer dream of matching. And within that capacity, the proximity fuse, known to the Allies as the VT fuse, stood out as a symbol of a deeper truth. This war was no longer a contest of courage, tactics, or ideology. It was a contest of numbers, and Germany was already behind by orders of magnitude. Becker read the first report. 40,000 fuses manufactured per day. 40,000, each one more intricate than anything German factories could assemble in a week. Each a miniature radar set designed to survive artillery acceleration, shocks, and environmental extremes, and to detonate with near-perfect precision. The Americans were producing at a rate that Germany could never match, even if every resource were redirected toward that single goal. And yet, Becker realized. They were producing these fuses alongside tanks, aircraft, ships, and conventional ammunition, simultaneously, without pause. He sat back in his chair, hands pressed against his face. He had expected superiority in technology, perhaps tactical surprises. He had not expected mathematics to decide the war. Becker called his senior staff again. They gathered in the same freezing warehouse, the shells lying silently on the examination table. No one spoke at first. Becker began pacing. Then he recited the numbers aloud, deliberately. Production rates, component tolerances, factory capacities, labor hours, material inputs. He calculated totals, outputs per week, monthly, and projected yearly. Every single figure pointed to the same horrifying conclusion. Germany could not keep pace. The room fell silent. Some engineers whispered among themselves. Some stared blankly at the shells. One younger engineer finally asked what everyone was thinking. "How can we fight this?" Becker did not answer immediately. Instead, he pulled a fresh sheet of paper and began tabulating comparisons. In 1944, Germany produced 40,000 aircraft. That same year, the United States produced 96,000. The Americans produced more fuses in a single day than Germany had produced aircraft in a year. They had already surpassed Germany's total output of nearly every weapon system, often by multiples. Tanks, trucks, artillery pieces, ammunition, they were all pouring from factories at a rate Germany could only envy from afar. He sat back in his chair, hands pressed against his face. He had expected superiority in technology, perhaps tactical surprises. He had not expected mathematics to decide the war. Becker called his senior staff again. They gathered in the same freezing warehouse, the shells lying silently on the examination table. No one spoke at first. Becker began pacing. Then he recited the numbers aloud, deliberately. Production rates, component tolerances, factory capacities, labor hours, material inputs. He calculated totals, outputs per week, monthly, and projected yearly. Every single figure pointed to the same horrifying conclusion. Germany could not keep pace. The room fell silent. Some engineers whispered among themselves. Some stared blankly at the shells. One younger engineer finally asked what everyone was thinking. "How can we fight this?" Becker did not answer immediately. Instead, he pulled a fresh sheet of paper and began tabulating comparisons. In 1944, Germany produced 40,000 aircraft. That same year, the United States produced 96,000. The Americans produced more fuses in a single day than Germany had produced aircraft in a year. They had already surpassed Germany's total output of nearly every weapon system, often by multiples. Tanks, trucks, artillery pieces, ammunition, they were all pouring from factories at a rate Germany could only envy from afar. He sat back in his chair, hands pressed against his face. He had expected superiority in technology, perhaps tactical surprises. He had not expected mathematics to decide the war. Becker called his senior staff again. They gathered in the same freezing warehouse, the shells lying silently on the examination table. No one spoke at first. Becker began pacing. Then he recited the numbers aloud, deliberately. Production rates, component tolerances, factory capacities, labor hours, material inputs. He calculated totals, outputs per week, monthly, and projected yearly. Every single figure pointed to the same horrifying conclusion. Germany could not keep pace. The room fell silent. Some engineers whispered among themselves. Some stared blankly at the shells. One younger engineer finally asked what everyone was thinking. "How can we fight this?" Becker did not answer immediately. Instead, he pulled a fresh sheet of paper and began tabulating comparisons. In 1944, Germany produced 40,000 aircraft. That same year, the United States produced 96,000. The Americans produced more fuses in a single day than Germany had produced aircraft in a year. They had already surpassed Germany's total output of nearly every weapon system, often by multiples. Tanks, trucks, artillery pieces, ammunition. They were all pouring from factories at a rate Germany could only envy from afar. He sat back in his chair, hands pressed against his face. He had expected superiority in technology, perhaps tactical surprises. He had not expected mathematics to decide the war. Becker called his senior staff again. They gathered in the same freezing warehouse, the shells lying silently on the examination table. No one spoke at first. Becker began pacing. Then he recited the numbers aloud, deliberately. Production rates, component tolerances, factory capacities, labor hours, material inputs. He calculated totals, outputs per week, monthly, and projected yearly. Every single figure pointed to the same horrifying conclusion. Germany could not keep pace. The room fell silent. Some engineers whispered among themselves. Some stared blankly at the shells. One younger engineer finally asked what everyone was thinking. "How can we fight this?" Becker did not answer immediately. Instead, he pulled a fresh sheet of paper and began tabulating comparisons. In 1944, Germany produced 40,000 aircraft. That same year, the United States produced 96,000. The Americans produced more fuses in a single day than Germany had produced aircraft in a year. They had already surpassed Germany's total output of nearly every weapon system, often by multiples. Tanks, trucks, artillery pieces, ammunition. They were all pouring from factories at a rate Germany could only envy from afar. He sat back in his chair, hands pressed against his face. He had expected superiority in technology, perhaps tactical surprises. He had not expected mathematics to decide the war. Becker called his senior staff again. They gathered in the same freezing warehouse, the shells lying silently on the examination table. No one spoke at first. Becker began pacing. Then he recited the numbers aloud, deliberately. Production rates, component tolerances, factory capacities, labor hours, material inputs. He calculated totals, outputs per week, monthly, and projected yearly. Every single figure pointed to the same horrifying conclusion. Germany could not keep pace. The room fell silent. Some engineers whispered among themselves. Some stared blankly at the shells. One younger engineer finally asked what everyone was thinking. "How can we fight this?" Becker did not answer immediately. Instead, he pulled a fresh sheet of paper and began tabulating comparisons. In 1944, Germany produced 40,000 aircraft. The war continued for months. Hundreds of thousands more would die. Becker's calculations, the shells on the table, and the stark truth of industrial imbalance were ignored. Yet for those who understood, for those willing to see beyond propaganda and myth, the conclusion was inevitable. Germany was losing, not because of bravery or strategy, but because arithmetic refused to be denied. Here is part 3, the final section, written in the same documentary-style narrative, continuous and immersive, completing the story, and designed to run around 4 Google Docs. It focuses on the strategic consequences of Becker's discovery, the scale of American production, the VT fuse's battlefield impact, and Becker's legacy. The frozen warehouse grew colder as winter deepened, but for Becker, the chill was no longer the pressing danger. The true threat had long passed beyond his hands. It was now the inexorable arithmetic of American industry. Every report he opened confirmed the same terrifying pattern. The United States was producing not only artillery fuses at staggering rates, but tanks, aircraft, ships, and munitions simultaneously, all while sustaining an army in the field half a world away. Germany, by contrast, struggled to maintain minimal output. Factories lay in ruins, supply chains were fractured, skilled labor had been replaced with coerced and inexperienced workers, and raw materials were increasingly scarce. Precision manufacturing, once Germany's pride, had become impossible at scale. Becker returned to his desk late one night, carefully reviewing battlefield reports from the Ardennes. Commanders consistently noted that artillery had become devastatingly effective, forcing German infantry out of entrenched positions and making conventional tactics useless. Foxholes no longer offered protection. Trenches became death traps. Entire defensive doctrines were rendered obsolete almost overnight. The VT fuse had not only multiplied firepower, it had rewritten the rules of survival on the battlefield. The calculations were clear. Every shell with a proximity fuse was equivalent to 3 or more conventional shells. Every artillery battery equipped with these fuses could deliver concentrated, precise, and devastating firepower against formations that previously would have survived sustained bombardment. In the Ardennes, these fuses had turned defensive positions into open targets. The Americans had achieved a force multiplication invisible to the naked eye, but undeniable in its effect. German soldiers, frozen and exhausted, could only watch as the battlefield itself seemed to conspire against them. Becker understood the scale. The United States had produced over 40,000 fuses per day, and the total production would reach more than 22 million in under 2 years. No other nation could match this, not even cumulatively. By the time German intelligence began to notice the scope of the problem, it was too late. The arithmetic was irreversible. The numbers did not lie, and they left no room for ideology, wishful thinking, or strategic pride. He wrote his final report with meticulous care. Every detail was precise, every figure verifiable. The conclusions were stark. The VT fuse represented a fundamental, decisive, and irreversible advantage. Germany could not counter it. They could not match it. They could not hope to overcome it. The war was lost, not through bravery, not through poor leadership, but because of production, innovation, and scale. The math itself condemned the Reich. When the report reached high command, it was dismissed. Officials called it defeatist. One officer scoffed, accusing Becker of allowing Allied propaganda to distort his judgment. Another argued that the fuses, while technically impressive, could be countered with strategy and skill. But Becker knew better. He had held the evidence in his hands. He had dissected the miniature radar sets. He had reviewed the production tables. He had done the arithmetic. Strategy could not overcome production at this scale. Skill could not defeat mathematics. And yet the war continued. Battles raged, cities burned, lives were lost. Becker's calculations went unheeded. German soldiers marched to their deaths, their leaders clinging to myth over reality. The VT fuse, small and unassuming, was delivering death on a scale that human courage could not withstand. It was a silent weapon, invisible until it struck, and utterly unforgiving. After the war, Becker's estimates were vindicated. Production figures were declassified, and historians confirmed that the Americans had indeed manufactured over 22 million proximity fuses in less than 2 years. The impact was extraordinary. At the Battle of the Bulge, Patton himself acknowledged that the fuses had decisively influenced the outcome. British analysts confirmed that artillery effectiveness had increased by 300%. One shell with a VT fuse was equivalent to 3 to 5 conventional shells. Entire strategies that had relied on entrenched positions became irrelevant. Becker reflected on a larger truth. The VT fuse was more than a weapon. It was a revelation of industrial power and the consequences of ignoring reality. Ideology, myths of superiority, and political arrogance could not compete with mathematics and production. Germany's failure was not merely military, it was systemic. The regime had chosen comforting narratives over empirical evidence, pride over practicality, and as a result, it had ignored the warnings Becker and others provided. In the quiet aftermath, Becker returned to his work, documenting, analyzing, and cataloging. He knew he had been powerless to change policy, but he also knew that history would eventually recognize the truth. The VT fuse had not only won battles, it had exposed the fatal flaw in the German war machine. Technology and production, applied relentlessly and intelligently, had become decisive. The human cost was staggering, but the lesson was clear. The mathematics of industrial warfare cannot be argued away, no matter how fiercely one clings to ideology. The war continued for a few more months. Cities fell, armies surrendered, and millions of lives were lost. Yet for those who understood Becker's work, the outcome had been predetermined long before the final guns fell silent. Germany had fought a battle that had already been mathematically decided. The VT fuse was proof. Evidence in hand, Becker had sounded the alarm, but the regime had refused to listen. And so the tiny shells resting on that frozen warehouse table became symbols of a larger truth. Victory belongs to those who combine innovation, production, and precision with strategy. Courage cannot change arithmetic. Ideology cannot override mathematics. And no matter how fiercely one fights, ignoring reality has consequences measured not in ideology, but in human lives and history itself. Becker lived to see the aftermath. He witnessed Allied occupation, reconstruction, and the declassification of the very data he had struggled to communicate. The numbers validated his warnings. The VT fuse was recognized as one of the most decisive technological contributions to the Allied victory. Battles were analyzed, reports written, lessons learned. History would remember the weapon. History would remember the mathematics. And Becker, quietly, understood that he had been right all along. The frozen warehouse outside Berlin, once a chamber of analysis and despair, had revealed a truth more devastating than any bomb. Germany had lost the war before ideology, valor, or strategy could save it. The Allied victory, forged in factories, laboratories, and intelligence bureaus, was inevitable. And the VT fuse, small, deadly, and precise, was the emblem of that irreversible advantage.